my dear students, welcome back to Brahmi tutorial. The topic for today is organic chemistry. So what is organic chemistry? Organic chemistry is a branch of science which deals with carbon compounds except oxides, carbonates and carbides. So why is carbon so special that there is a separate branch of chemistry for the study of its compounds? Why is carbon so unique among all elements? Carbon is unique due to its three properties, which is also known as the unique nature of carbon. The three properties of carbon which makes it so special among all elements are tetravalency, catenation and isomerism. So what is tetravalency? Tetravalency means the valency of carbon is 4, which we already know. Catenation. Catenation means its ability of carbon compounds to form chains. We know that carbon forms single bond, double bond and triple bond. Due to these bonds, it can form long chains, which is also known as catenation. Now, what is isomerism? Isomers are organic compounds having same molecular formula but different structural formula. This phenomenon is known as isomerism. We'll get to know more about isomerism and isomers further in the chapter. Now let's see the classifications of compounds. Compounds are classified into organic compounds and inorganic compounds. Organic compounds are the carbon compounds except oxides, carbonates and carbides, where the other compounds are classified as inorganic compounds. Now under organic compounds we have two types, aliphatic and aromatic. And aliphatic means the carbon here in the compound, the carbon atoms are arranged in straight chains or branch chains, which is known as open chain structure. So the carbon compounds, the organic compounds having open chain structure is known as aliphatic organic compounds. Now what is aromatic organic compounds? Aromatic organic compounds means in these compounds the carbon atoms are arranged in closed chain. So these organic compounds are known as aromatic organic compounds. Now under aliphatic organic compounds we have hydrocarbons. As the name says, hydro and carbons, which means the organic compounds having only hydrogen and carbon. Under hydrocarbons we have two subdivisions. One is saturated hydrocarbons, another is unsaturated hydrocarbons. Saturated hydrocarbons means where in this hydrocarbons the whole carbon the carbon atoms are fully, the valency of the carbon atoms are fully satisfied by only single bond. That is known as saturated hydrocarbons. Now what is unsaturated hydrocarbons? Unsaturated hydrocarbons means where the carbon atoms are the valency of the carbon atoms are not fully satisfied by single bond. Instead, they are double bonds and triple bonds in this hydrocarbons. Example for saturated hydrocarbons is alkanes. An example for unsaturated hydrocarbons is alkenes and alkynes. Now what are these two subdivisions of aromatic organic compounds? The two subdivisions between the aromatic organic compounds are homocyclic aromatic compounds and heterocyclic. Now we don't need to know in detail about homocyclic and heterocyclic organic compounds. We just need to know the examples. Example for homocyclic aromatic compounds are benzene, and example for heterocyclic is pyridine. Now let's know what is homologous series. Homologous series is a series of organic compounds where the successive members follow regular structural pattern, successive compounds differing by CH2 group. Now what is it? is just a series of organic compounds. It's a series of organic compounds where the two consecutive members or two consecutive compounds follow a regular structural pattern. In the structure, there is a particular pattern. They follow the pattern and successive compounds differing by CH2 group. For example, examples are alkenes and alkynes. Now for example, in alkenes, we have methane, which is CH4, and we have ethane, which is Ce2H6. Now if we see, they both differ by CH2 group. So this series is known as homologous series, where two consecutive members differing by CH2 group. So what is homologous series? Homologous series is a series of organic compounds where the successive members follow a regular structural pattern and successive compounds differing by CH2 group. The examples are alkanes, alkenes and alkynes. Now let's know the members under alkanes, alkenes and alkynes. The general formula of alkane is CnH2n plus 2. The general formula of alkene is CnH2n. The general formula of alkyne is CnH2n minus 2. So when n is 1, the root word is meth. For the first member of alkane is methane. So when n is 1, C is 1. So H is 2 into 1 is 2. 2 plus 2 is 4. So the formula is CH4. The corresponding member for alkene and alkyne is not there. So when n is 2, now when n is 2, the root word will be eth. So the second member of alkane is ethane. Formula is C2H2 into 2 4. 4 plus 2 is 6. So C2H6. The first member of alkane is ethene. The first member of alkene is ethene. Formula is H2 into 2 4. So it is C2H4. So the first member of alkyne is ethyne, which is C2H2 into 4. 4 minus 2 is 2. So the first member of alkyne is ethyne. Formula is C2H2. Now when n is 3, the root word will be pro. The third member of alkane is propane. Formula is C3H2 into 3 is 6. 6 plus 2 is 8. So C3H8. The second member of alkene is propene. Formula is C3H2 into 3 6. So the formula is C3H6. The second member of alkyne is propyne. Formula is C3H2 into 3 6. 6 minus 2 4. So the formula is C3H4. So when n is 4, the root word will be bute. So the fourth member of alkane is butane. Formula C4H2 into 4 8. 8 plus 2 10. So formula is C4H10. The third member of alkene is butene. Formula C4H2 into 4 8. So formula is C4H8. The third member of alkyne is butyne. Formula C4H2 into 4, 8, 8 minus 2, 6. Formula C4H6. So when N is 5, the root word is pent. The fifth member of alkane is pentane. Pentane. Formula C5H2 into 5, 10. 10 plus 2, 12. Formula C5H12. So the fourth member of alkene is pentene. Formula C5H2 into 5, 10. Formula C5H10. The fourth member of alkyne is pentyne. Formula is C5H2 into 5, 10, 10 minus 2, 8. Formula C5H8. For the board exam, we have to know all the members of alkane, alkene and alkyne till pentane, pentene and pentyne. So in alkanes there is single bond. In alkene there is one double bond, rest all is single bond. Now on alkyne one bond is triple bond and rest all is single bond. So in alkane is single bond, alkene double bond and alkyne triple bond. Now let's know what is alkyl group. Alkyl group is the group derived from by the loss of H hydrogen atom from apparent alkene. So when we remove one hydrogen atom from the parent alkene, we get alkyl group. So for example, ethane C2H6 minus H, we get ethyl, which is C2H5. So C3H8 propane, if we take out one hydrogen, we get C3H7, which is propyl. This is known as the alkyl group. Now let's know about functional groups. And functional group is an atom or radical or a bond which defines the structure of organic compounds and confers characteristic properties to it. So functional group, it is an atom or it can be an atom such as fluorine, here as it just highlights, like fluorine, bromine, iodine, or it can be a radical such as hydroxyl group or bond which defines the structure of organic compounds and confers characteristic properties to it. This is a definition of functional group. Examples are hydroxyl. Hydroxyl is the alcohol group, OH. Next is aldehydes. Aldehyde, the formula CHO or C double bond O single bond H. Halides are halogens such as fluorine, chlorine, bromine or iodine, and carboxylic acid formula COOH or C single double bond O single bond OH. Now let's move forward. Now we know already about the molecular, we know about formulas. There is molecular formula, we already know that. So for example, we have propane. Molecular formula of propane is C3H8. Now after molecular formula, there is another type of formula for organic compounds that's called structural formula. Structural in molecular formula just showing the number of atoms of each element. For example, in propane we have 3 carbon atom and 8 hydrogen atom. In structural formula, we get to know how these atoms are arranged. Under structural formula, we have two types of formula. One is branched structural formula and one is condensed structural formula. Branched structural formula shows the actual arrangement of atoms in the compound. Now, for example, molecular formula of propane is C3H8. Now, this branched structural formula of propane is, I've drew here. So there are 3 carbon atoms and 8 hydrogen atoms. This shows the arrangement of carbon and hydrogen atoms in propane. This is called a branched structural formula. Now in condensed structural formula, we are just showing the linking of carbon atoms, not the hydrogen atoms. Here we are shown how the hydrogen atoms and carbon atoms are arranged. in branched structural formula. In condensed structural formula, we are showing how the carbon atoms are arranged. Now, the condensed structural formula of propane is H3C, CH2, CH3. In all cases, in all the formula, the number of carbon atoms and number of hydrogen atoms of propane is same. Now let's learn more about isomerism. Now, for example, I've taken butane, which is formula C4H10. In butane, there are two isomers. One is N-butane and another is isobutane. We know that what are isomers? Isomers are organic compounds having the same molecular formula but different structural formula. Now, butane, these are the two isomers of butane. They have the same molecular formulas. If you see, we have 4 carbon atoms and 10 hydrogen atoms in both the cases. But the structural formula, the way they have arranged, is different. For example, in N-butane, the carbon atoms are in the straight line. But in isobutane, 3 carbon atoms are in straight line, but there is a branched carbon atom here. So, even though they have the same structural formula, they have the same chemical properties, but the arrangement of carbon atoms is different. So, these are the two isomers of butane, which is N-butane and isobutane. This is what isomers are called. Now, under isomers, we have 3 different types. First is chain isomers, second is position isomers, and third is geometric isomers. Now, let's know what is chain isomers. Chain isomers are formed due to the difference in arrangement of carbon atoms in the bond. For example, we have already seen that in chain isomers are formed due to difference in the arrangement of carbon atoms in the bond. For example, if the carbon in one isomer, the carbon atom will be straight, whereas in the other isomer, the carbon atom may be branched. So these type of isomers are known as chain isomers. Next, position isomers. Position isomers are formed due to the difference in arrangement of double bond or triple bond. For example, if double bond, for example, between the first 2 carbon atom, if there is a double bond in one isomer, in another isomer the double bond might be between second and third carbon atom. Due to the change in the double bond or triple bond, there are 2 isomers formed. So these isomers is known as position isomers. Next, the geometric isomers. Geometric isomers happen due to the difference in arrangement of atoms around the double bond. For example, these two are examples of geometric isomers. So see here 2 carbon atoms. There are 2 carbon atoms having double bond. One we have CH3 one side here H, here hydrogen, and here CH3. In another isomers, there is in the both side there is hydrogen, and on another side there is CH3 CH3. Due to difference in, because you here in this isomer CH3 is here and H is here, but in this isomer H is here and CH3 is here. Due to the difference due to the change in position of CH3 and H around the double bond, there because the change of CH3 and H around the double bond, these two isomers are known as geometric isomers. Now let's know the isomers of alkanes. First is for methane, ethane and propane, we don't have any isomers. Now next is butane. For butane, we have 2 isomers. The common name of the 2 isomers is N-butane and isobutane. The IPSC name of these 2 isomers is, this is butane and this is 2-methyl propane. Now let's draw them. Now first we'll draw N-butane. This is the structure of N-butane. Now let's draw isobutane. This is the branch structure of isobutane. Now let's draw the isomers of pentane. In alkenes, the isomers of alkenes are chain isomers. Butane has chain isomers and pentane has chain isomers only. Now there are three isomers of pentane. First is N-pentane, second is isopentane, and third is new pentane. N-pentane is known as pentane, and the IPSC name of N-pentane is pentane. The IUPAC name of isopentane is 2-methyl-butane, and the IUPAC name of new pentane is 2,2-dimethyl-propane. Now let's draw N-pentane. Now let's draw, this is N-pentane. Now let's draw isopentane. This is isopentane. Now let's draw new pentane. This is new pentane. Now let's draw the isomers of alkenes. In alkenes, we are taking only one alkene, which is butene. Butene has all the three types of isomers: chain isomers, position isomers, as well as geometric isomers. Now first let's know the chain isomers of butene. The chain isomers of butene is 1-butene and 2-methylpropene. Let's draw first 1-butene. This is 1-butene. Now, 1-butene needs where to put the double bond. The double bond is here. Since it is 1-butene, the double bond is between the first carbon atom and the second carbon atom. So this is 1-butene. Now let's draw 2-methylpropene. Now where to put the double bond? Here we can put the double bond wherever we want. I will put the double bond between the first carbon atom and the second carbon atom. So this is 2-methyl propene. Now let's know the position isomers of butene. For butene there are two position isomers. First is 1-butene and second is 2-butene. Now let's draw 1-butene. Now for 1-butene, the double bond should be between the first carbon atom and the second carbon atom here. Now this is 1-butene. Now let's draw 2-butene. Now for 2-butene, the double bond should be between the second carbon atom and the third carbon atom. So this is 2-butene. Now let's see the geometric isomers of butene. Now for butene we have two geometric isomers again. First is 2-butene cis and 2-butene trans. This is 2-butene cis CIS and this is 2-butene trans TRANS. So let's draw 2-butene cis. This is 2-butene cis. Now let's draw 2-butene trans. This is 2-butene trans. Now for cis, the same side has hydrogen and same side has CH3 for 2-butene cis. For 2-butene trans, this in the alternate side there is CH3 and alternate side there is H. Now let's know the isomers of alkynes. For alkynes there is only position isomers. First we'll for ethyne and propyne there is no isomers. So next is butane. For butane there is two isomers. One is 1-butane and second is 2-butane. They are both the position isomers of butane. So let's draw first 1-butane. For 1-butane, this is C4. So for 1-butane, the triple bond should be between the first carbon atom and the second carbon atom. So this is is 1-butene. Now let's draw 2-butene. For 2-butene, the triple bond should be between the second carbon atom and the third carbon atom. So this is 2-butene. These are two position isomers of butene. Next, let's draw the isomers, the position isomers of pentane. So there are only two position isomers of pentane. One is 1-pentane and the second is 2-pentane. So first let's draw 1-pentane. The triple bond of 1-pentane is between the first carbon atom and second carbon atom. So this is 1-pentane. Now let's draw 2-pentane. So the triple bond of 2-pentane is between the second carbon atom and third carbon atom. So this is 2-pentane. So these are the position isomers of pentane.